Hello everyone, welcome to this challenge question walkthrough for Edexcel's Core Pure Year 1 textbook, Chapter 4. Okay, so here we have our first question from exercise 4b. We've got alpha, beta and gamma being the roots of the equation here, the general cubic equation, where we have x being a member of the complex numbers and a, b, c and d being real numbers. By considering all of the possible cases in which alpha, beta and gamma are real or complex, explain why the following are always real numbers. And here we've got the sum of the alphas, sum of the alpha betas, and alpha beta gamma. Okay, so I guess the first thing we can note is that for any polynomial with real coefficients, like this cubic here, then we must have all complex roots occurring in conjugate pairs. Okay, so that means for a cubic with 3 roots, there are only 2 options. We can either have alpha, beta and gamma all being real, or we could have alpha or we could have one of the roots, say alpha, being real, and then the other 2 form a complex conjugate pair. Okay, and let's say beta is equal to p plus qi, which means that gamma must then equal p minus qi, where p and q are real numbers. Okay, so let's start with part A, alpha plus beta plus gamma. So, okay, alpha is a real number, so let's leave it as it is. Beta, let's replace with this p plus qi, and then the gamma we can replace with p minus qi. These 2 I terms cancel, so we're just left with alpha plus 2p, which is real. Then for the sum of the alpha betas, we're going to have alpha times beta, which is p plus qi, plus alpha times gamma, which is p minus qi, plus beta times gamma, which is p plus qi times p minus qi. And now if we expand these brackets, we're going to have alpha p plus alpha qi plus alpha p minus alpha qi plus here p squared minus q squared I squared, because it's a difference of 2 squares. So we're going to see here some cancelling again with the alpha qi's. Then we're going to have 2 alpha p, and this p squared. Then I squared is just minus 1, so it's just plus q squared. And again, this is now a member of the real numbers because there are no imaginary terms. So we proved it for the sum of the alpha betas. Finally, let's look at alpha beta gamma. Well, this is going to be alpha times p plus qi times p minus qi. You can see where this is going. This is then going to be equal to alpha times p squared minus q squared I squared, or just plus q squared, which is real, as required. And the last thing we need to note before we finish is that for the case where we have alpha, beta and gamma all being real, it is obviously the case for all 3 of these expressions that they are real. And that's all we need to do to finish off. Okay, from exercise 4e, we've got the quartic equation here, 2x to the power of 4 minus 3x cubed plus x squared minus 2x minus 6 equals 0, and has the roots alpha, beta, gamma and delta. For part A, we're asked to find an equation with integer coefficients that has roots 2 alpha plus 1, 2 beta plus 1, 2 gamma plus 1, and 2 delta plus 1. So this is just a routine question. We can let the variable w equal 2x plus 1, and then rearrange to find x to plug it back into the original equation. So we're going to have x equals w minus 1 over 2. Plugging that into the original equation, so we have 2 lots of w minus 1 over 2 to the power of 4, minus 3 lots of w minus 1 over 2 to the power of 3, or cubed, plus w minus 1 over 2 squared, minus 2 times w minus 1 over 2, minus 6 being equal to 0. And now we can multiply through by 8 to get rid of the fractions. So here we're going to have 16 lots of this, which is just w minus 1 to the power of 4. Then we're going to have just 3 lots of w minus 1 cubed. Then we're going to have just 2 lots of w minus 1 squared. Then we're going to have 8 lots of w minus 1. Take away 6 times 8, which is 48. That equals 0. And then using binomial expansion, very carefully, so w to the power 4, take away 4w cubed, plus 6w squared minus 4w plus 1. Then we're going to have minus 3 lots of, so w cubed is the first term, so minus 3w cubed. Then the next term is minus 3w squared, so it's plus 9w squared. Then we're going to have plus 3w, so minus 9w. Then minus 1 gives us plus 3. Then we've got plus 2 lots of w minus 1 squared, so that's plus 2w squared minus 4w plus 2. Then we've got minus 8w plus 8, minus 8w plus 8, minus 48 to add on to the end, but I couldn't fit it down there because of space. Let's say it's equal to, down here, we've got w to the power 4, minus 7w cubed. Then we've got 6 plus 9 plus 2 is 17w squared. Then we've got minus 4 minus 9 is minus 13, minus 17 minus 25w, plus 1 plus 3 plus 2 is plus 6, plus 8 minus 48 is minus 40, so minus 34. And that is equal to 0. Okay, then for part B, we were asked to sketch the approximate locations of the roots of the new equation. Well, we're just going to multiply each of these roots already on the diagram by 2 and then add 1. So for this first one here, if we extend the real axis, we multiply this by 2, we're going to end up at 4. Then add 1, we're going to end up at 5. For the minus 1, if we multiply that by 2, we're going to end up at minus 2. Add 1, that's just going to be minus 1 again. So let me rub out that cross there. So we've got 1 at minus 1 again, 1 at 5 here on the real axis. Then this up here is going to be, if we multiply by 2, it's going to end up somewhere here. Then we're adding 1, so we're going to end up around here. And very similarly for the one down at the bottom there, if we multiply by 2, we're going to end up somewhere here. Adding 1 ends up here. Okay, so those are our new roots. So the exact locations are minus 1 and 5 on the real axis, and the approximate locations for these two are around there. Okay, and finally for the mixed exercise 4, our first question is this cubic equation here having roots alpha, beta and gamma, and we're asked to find a cubic equation with the roots 1 over alpha plus 1, 1 over beta plus 1 and 1 over gamma plus 1. So here we can again use a substitution. So let w, the new variable, equal 1 over x plus 1. Then we can rearrange for x. So wx plus w is equal to 1. So x is equal to 1, take away w, divided by w. And we can substitute that back into the original equation now. So 1 minus w over w cubed plus 4 times 1 minus w over w squared. Minus 5 times 1 minus w over w, minus 7 is equal to 0. Then you can multiply through by w cubed to get rid of the fractions. So 4w, 1 minus w squared here, minus 5w squared, 1 minus w, minus 7w cubed. Now expanding the brackets using binomial expansion. So 1 take away 3w plus 3w squared minus minus w cubed. Then we've got plus 4w, minus 2w times 4w is minus 8w squared, plus w squared, so that's 4w cubed. Then we've got minus 5w squared plus 5w cubed, and finally minus 7w cubed. So the w cubed terms are minus w cubed, 4w cubed and 5w cubed, and the minus 7w cubed is at the end. So in total that is 1 lot of w cubed. Then we've got the 3w squared here, minus 8w squared, minus 5w squared. So that will give us minus 10w squared. Then for the w terms, you've got the minus 3w plus 4w, and that's it. So that's plus w, And finally, the 1 on the end gives us this cubic. Okay, so for question 2, we've got the cubic equation here, which has roots alpha, beta, and gamma. Without solving the equation, find an equation that has roots alpha plus beta, beta plus gamma, and gamma plus alpha. So here, unfortunately, there's no direct substitution we can use because the roots for the new equation are given in terms of different pairs of the roots of the original equation. There is an alternative method for these sorts of questions that you can see in textbooks and you can see in mark schemes, which is to find the sum of the alphas, the sum of the alpha betas and alpha beta gamma for the original equation, and then find them for the new equation with the new roots, and then use the values that you get from this up here in the expressions for the new roots. And I'll show you what I mean by that in a second. But first, let's find alpha, some of the alphas, some of the alpha betas, and alpha beta gamma for the original equation. So I'll write that in red here. So the original equation, we have the sum of the alphas is minus b over a. A here is equal to 1, so it's just minus b, so minus 2. The sum of the alpha betas is going to be equal to c over a, or just c, so that's minus 3. And then finally, we have alpha beta gamma is going to be equal to minus d over a, or just minus d, which is 5. Okay, so these we will be using in a second. Now let's have a look at the new equation with the roots alpha plus beta, beta plus gamma, and gamma plus alpha. If we then look at what the sum of the alphas are for the new equation, that's going to be alpha plus beta plus gamma plus alpha. And you should see that this is going to be 2 lots of alpha plus beta plus gamma. I should really put dashes here because this is the sum of the alphas for the new equation. This is going to be equal to 2 times the sum of the alphas for the original equation, which is 2 times minus 2, which is minus 4. And this tells us that minus b over a for the new equation is going to be equal to minus 4. Okay, let's now do the same for the sum of the alpha betas. For the new equation, that's going to be alpha plus beta times beta plus gamma, plus alpha plus beta times gamma plus alpha. And finally, we're going to have our beta plus gamma times gamma plus alpha. Now, if I expand all these brackets out and write them strategically, we're going to have alpha beta plus alpha gamma plus beta squared plus beta gamma. Then we're going to have plus alpha gamma plus alpha squared plus beta gamma plus alpha beta. Then we're going to have, for the final bracket, beta gamma plus alpha beta plus gamma squared plus alpha gamma. And you can see from the way I've written it there, this is going to be 3 times alpha beta plus alpha gamma plus beta gamma. And then we're going to add 1 lot of alpha squared, 1 lot of beta squared, and 1 lot of gamma squared. So this is going to be equal to 3 times the sum of the original alpha betas plus the sum of the original alpha squared. And we can use the formula for the sum of alpha squareds, which is the sum of the alphas all squared. Then we're going to take away 2 lots of the sum of alpha beta, sum of the alpha betas. And that's true for quadratics, cubics, and quartics. So here we go. Using the original equation, the sum of the alphas is minus 2 all squared, and the sum of the alpha betas is minus 3. So we're going to have 4 plus 6, which is 10. So let's replace this sum of the alpha squared with 10. So we're going to have something plus 10. For the 3 times the sum of the alpha betas, that's going to be 3 times minus 3 from up here. So 3 times minus 3 gives us minus 9. Minus 9 plus 10 is 1. So now we know that C over A in the new equation is going to be equal to 1. Okay, and finally, we just need to find out what alpha, beta, gamma for the new equation is. So that's alpha plus beta times beta plus gamma plus gamma plus alpha. Sorry, times gamma plus alpha. And if we expand all this out, let's do the first bracket first. We have alpha beta plus alpha gamma plus beta squared plus beta gamma times gamma plus alpha. Now expanding these last two brackets, we've got alpha beta gamma. Then we've got plus alpha squared beta, then we've got plus alpha gamma squared, then alpha squared gamma, then beta squared gamma plus alpha beta squared plus beta gamma squared plus alpha beta gamma. So, first of all, I notice that we've got these two alpha beta gammas, and then this in the middle here. Now for this expression, I'm thinking we can use these top two from the original equation, and I'm thinking we might be able to multiply them together. So let's see what happens if we do that. Then we're going to have the sum of the alphas times the sum of the alpha betas. So alpha beta plus beta gamma plus gamma alpha. So the reason why I thought this might be a good idea is because you can see we're going to get the alpha squared beta from the first two terms. Then we're going to have alpha beta gamma. Then we're going to have alpha squared gamma, which is another term from up there. Then we're going to have alpha beta squared, which is another term from up there. Beta squared gamma, another term. Alpha beta gamma. And then we're going to have alpha beta gamma again, plus beta gamma squared, plus alpha gamma squared. So actually what this is what we've got in purple up there. So the alpha squared beta plus alpha gamma squared plus alpha squared gamma plus beta squared gamma plus alpha beta squared plus beta gamma squared. That's all the purple stuff from up there. From these terms here. All we've done to that is added 3 alpha beta gamma. So to find that purple bit, so just to save time, we're going to write that's the purple bit. That's going to be equal to, well, the sum of the alphas times the sum of the alpha betas from here, and then we're going to take away 3 lots of alpha beta gamma. So that is equal to, well, minus 2 times minus 3 times 5, which is 6 minus 15, which is minus 9. So this purple bit there, we can take away 9 from here. 2 times alpha beta gamma is 10. Take away 9 is 1. So from there, we know that the final piece of the puzzle is that minus d over a is equal to 1. And finally, we just need to write the new equation. We can let a be whatever we want. So let's say a is equal to 1 to keep things simple. And the reason why we can do that is because we can just divide any cubic through by whatever a would be to get a cubic with 1 as the coefficient of x cubed. So we can let a equals 1 with no problems whatsoever. Okay, so then we'd have minus b being equal to minus 4. So b is equal to 4. Then c would be equal to 1, and d would be equal to minus 1. So our cubic in terms of w would be w cubed plus 4w squared plus w minus 1 is equal to 0. Just a quick note as well, there is a way that you could have possibly done this with substitution instead, but it requires a little bit more insight. And the way we could have done it is to say, okay, we know that from the original equation the sum of the alphas is going to be equal to minus b over a, which is minus 2. So alpha plus beta plus gamma, we then know is going to be equal to minus 2. So alpha plus beta is then going to be equal to minus 2 minus gamma. And the same for beta plus gamma, that is going to then be equal to minus 2 minus alpha. And then alpha plus gamma is then equal to minus 2 minus beta. So a substitution we could have made using that little bit of insight here is that the new root is equal to minus 2 minus the old root. Okay. And then we could have followed on from there as usual. But here's an alternative method which I think is easier to come across. Okay, and for our final question from mixed exercise 4, question 3, the quadratic equation here has roots alpha, beta, gamma, and delta. By using a substitution or otherwise, find an equation that has roots alpha squared plus 1, beta squared plus 1, gamma squared plus 1, and delta squared plus 1. So let's follow what the question says and use the substitution here. W equals x squared plus 1. And rearranging for x, here we can see we're going to need a square root. So x is equal to the square root of w minus 1. And let's plug that back into the original equation. So x to the power of 4 is then going to be just w minus 1 squared. 2x squared is then going to be 2 times w minus 1. Then we've got 5 times the square root of w minus 1 plus 2 is equal to 0. Now if we expand the left-hand side out, so here we have w squared minus 2w plus 1 plus 2w minus 2. Take away 5 times the square root of w minus 1 plus 2 is equal to 0. So here the 2w's will cancel, the minus 2 and the plus 2 will cancel, so we're left with w squared plus 1 being equal to, if we take the minus 5 times the square root of w minus 1 to the right hand side, then that equals positive 5 times the square root of w minus 1. Now at this point we can square both sides, and I'll tell you why we can square both sides without worrying about adding any extra solutions in. So then we're going to have w squared plus 1 all squared being equal to 25 times w minus 1. Expanding the left hand side, we're going to have w to the power of 4 plus 2w squared plus 1 being equal to 25w minus 25. So our final answer is then going to be w to the power of 4 plus 2w squared minus 25w plus 26 equals 0, and that's our final answer. And just returning back to the point about not including any extra solutions, well, originally we had these 4 solutions, alpha, beta, gamma, and delta, to this quartic. Then we've used a substitution to find an equation that has the roots here. And because we've ended up with another quartic, we know that we definitely have exactly 4 roots, whether they're repeated or not, complex or not. We're going to have exactly 4 roots. So each one of these original roots corresponds directly to one of the other ones, because there's exactly 4 roots for the first equation and exactly 4 roots for our final equation, so we can square at this point with no issue. And that's the end of this challenge question walkthrough. Thank you for watching. I hope you enjoyed the video, and I hope to see you again soon.